Hi friends, welcome back. So today's lecture will see the transfer function of the state model. Okay, then we'll solve the solution of the state equation, and at last we'll see the controllability and observability. Then the state space analysis will be over. Okay, so today our intention is to find out the transfer function to the state model. Okay, the heading is the transfer function to state model. Okay friend, this one is very important. Why? If you find out the previous year gate papers for electrical instrumentation and electronics and communication, 60% questions you will find out from this area only. Find out the transfer function, you will be given with the state model, means A, B, C, everything will be given to you. Yes, and they will ask what is the transfer function, or what is the characteristic equation, or what are the poles, what are the roots. Everything we are going to discuss in this today. Okay, so the question is, the transfer function formula is given if you have, okay, let me write the equation first, then I'll come to the transfer function. Okay, so the equation is like the state space equation I'm writing, plus bu, here the output equation, that is cx plus du. You have in your hand this. Now you are calculating the transfer function based on your model. So this transfer function is given by si minus a inverse, you will multiply c here, b here, plus d if you have d value. Okay, so you know very well what is the A inverse. A inverse is nothing but adjoint A divided by determinant of A, isn't it? So similarly you can write this also. This is nothing but adjoint of what? Si minus A, isn't it? Divided by determinant of Si minus A. Okay, yellow, B plus D. Okay, this is very important formula because 60% questions rely on this. Okay, now the thing which you can make mistake, you can take this B you can take over here, and C you can take over here. This will be wrong. The format is this only: C, Si minus A inverse, and B. Okay, and you know very well in the matrix AB is not to be BA, isn't it? So this is not commutative. Am I right? This is commutative. Okay, you will check it. This is part of mathematics, so I'm not giving you guarantee. Okay, so this is the formula, a very famous formula. Again, I'm writing this formula for you. That is C Si minus A inverse B plus D. This is transfer function. Okay, in this transfer function, the denominator, if you will open this, you will observe you are getting Si minus A, isn't it? Si minus A, determinant of Si minus A. If you will equate this with a 0, this will give you characteristic equation. This is nothing but our characteristic equation. Okay, good, very important thing. Out of that 60%, 20% based on characteristic equation only. So if you will solve this equation, you will find out some poles, roots. So roots of this equation is nothing but the poles of system. The poles of system is nothing but the roots of this equation. Okay friends, so this roots also we call the eigenvalues for this. Here we are saying the eigenvalues of this also. Okay, now I'll take one example, so everything will be clear to you. So here is the question. This is A given. Okay, and let me complete it. x1, x2, plus 3 and 5 and u, and y also given 1 1 x1 x2. This is the entire equation given. Okay, now the formula for the transfer function is C first, Si minus A inverse second, and B here. No D is given, so it's a 0. Okay, so the Si minus A inverse you have to construct adjoint A divided by determinant of A, the value of this. Okay, in which you multiply with C and B. I think 3 or 4 times directly they ask the transfer function only. They have given like this: what is the transfer function of the given steady space model, in which everything is given in the equation form only. X dash like Ax plus Bu and y equal to Cx plus du. What is the transfer function? 3 times I think. So this is the transfer function equation. Okay, so adjoint A divided by mod A. So let's construct first Si minus A. Si minus A. So Si minus A, if you construct Si means S0 minus A. A is minus 2 minus 3 4 2. So Si minus A, that is S plus 2 3 and minus 4 is minus 2. This is your Si minus A matrix. Now you will find the inverse of this. So Si minus A inverse, what you have S plus 2 minus 4 3 is minus 2. Okay, so determinant of A is, the determinant of this I am going to find directly. This is S plus 2 S minus 2 minus plus 12. Okay, so open it, you will get S square plus 8. That is over. Now adjoint A. How to find adjoint A? I think you know very well. Adjoint A means adjoint of this Si minus A. Si minus A. Okay, so can I do directly here? This is the part of mathematics, and I hope that you people know already, isn't it? For order 2 cross true, you have to just interchange these two. S minus 2 will come here, S plus 2 come here, and you will change the sign of this 2. Minus 3 and this will become 4. Okay, and entire inverse now the inverse of this will be this divided by this. So let me come over the transfer function equation now. S minus 2 S plus 2 minus 3 divided by 4 and divide by S square plus 8. Here C is 1 1. Here B is 3 and 5, isn't it? Okay, so now you will multiply inside. Now you will multiply inside these two. What you will get is, you will get finally, can I write the final? Okay, just multiply this into this, then you will multiply this 3 and 5. So matrix multiplication you can do. You all are the smart, right? Smart people, smart students, hard working on the ATM, I hope. So what you will get is 1 plus it is divided by S square plus 8. This is nothing but your transfer function. If you solve this, you will get this. Okay, now what is the characteristic equation? The characteristic equation is nothing but S square plus 8, and the roots of this characteristic equation is nothing but the eigenvalues or the poles of the system. So S square plus 8 equal to 0. The poles will be S equal to plus minus J under root 8. Okay, so these are like this: J root 8 minus J root 8. So this system is marginally stability. marginal stable system. So you can conclude or you can come over the stability condition also, isn't it? So this system is a marginally stable system. So this is the procedure to find out the transfer function. Very important. I'll cover some more questions while solving the gate problems. Okay, now we'll come directly to the solution of the state model equation. Solution of the state model equation. Let's take the state equation. Here this is the state equation, not output equation. Okay, this is the state equation, state vector ax plus bu. You know very well this x is nothing but the state variable. This is state matrix, input variables, and this is the state vector. Overall this is the state equation. Okay, now very well you can by Laplace method you can do it, isn't it? By Laplace method, this is how you can write the derivative in the Laplace domain. This will be x into xs minus x0. I think you people will be agree with me, isn't it? You know, dxt by dt by Laplace you can write it x xs minus initial conditions kind of. Okay, so I can write this over here. What about this? AXS I can write, and this thing I can write PUS. Okay, take this XS term this side. So what you will get, this S and this A, so SI minus A. So this S is direct term, so you will convert into the matrix form. So it will be SI minus A. The matrix of order same as A. Okay, and XS outside, and this side you have BUS already you have, and this term will come to this side, so it will be X0. Now XS is, what is the XS? This is XS. I need the solution, means XT. We are looking for the XT. What is the XT? Solution in the time domain, isn't it? It's kind of, you know, the differential equation solution. In the differential equation solution also, if the differential equation is given like this, 3yt, this is yt equal to something, so we are looking for the solution yt. Similarly, we are looking for the xt here. So xs is nothing but this thing will come in denominator, and it will become like si. Okay, x0, wait a minute, this is x0 si minus a here, isn't it? And us, this one is nothing but si minus a. Now this will go up, I can take inverse, so it will become, your equation will become xs is nothing but si minus a inverse multiply with x0. Okay, and the remaining one is this is si minus a inverse into bus, isn't it? But you need the xt, so you will take inverse Laplace. So when you will take the inverse Laplace, you will get xt, and your xt will be for this L inverse of what? Si minus a inverse multiply with x0 plus L inverse of si minus a inverse b into us. So two things in the solution. This is the general solution of the state equation. What is this? This is the solution of state equation. So the solution is comprised by two set of equations. One is this and another is this. So what these are? This we call the zero input response. Zero input response. What zero input response means? When input is zero, The output you are getting because of the initial stage or initial condition. See, x0 is nothing but the initial condition. No input you applied. That's why 0 input response. The response because of the initial condition. So 0 input response, you can call it the response. The response because of initial conditions. Initial values. Okay, and this we call, here no initial condition is there, so here this is the zero state response. Now state is 0. This is the initial state. I'll call it initial state, so it will be clear to you people. Okay, so this is the response because of the 0 state, means state is 0 because of input. So I can call it because of input response. So 0 state response is nothing but the input response, and this one is 0 input response is nothing but the state response, isn't it? So in the final conclusion I can write xt is nothing but ZIR, 0 input response plus 0 state response. Okay, 0 input response is due to initial states, isn't it? And this is due to 0 state, means due to input. Any problem? So this is the solution of state equation. Another method I have, the classical method, I can say everything will be in the form of exponential. Classical method means nothing, you will take the everything in the exponential term. How you will solve that? See, you will convert the final in the t domain, so it will be e to the power at x0, isn't it? 1 divided by si minus a inverse you had right here. So when you will take the L inverse, Laplace inverse, this is in the denominator, so it will become e to the power at, isn't it? And x0 as it is, though this is the constant. So e to the power at x0 plus the next will be 0 to t e to the power a t minus tau b u tau d tau. Why this integration is coming? Because you have us in this equation. Us is nothing but 1 by s, so 1 by s, and this entire thing, because of 1 by s you will get the integration in the time domain, we know very well. And this is the part of that particular si minus a inverse, isn't it? So this thing is nothing but the ZSR, and this is nothing but the ZIR. Okay, now from this solution we are getting very interesting 30% question covered by this formula, whatever I'm going to write over here, that is the transition matrix phi t. If you will consider this e to the power at only, this thing if you are going to consider this, I call the state transition matrix, or in the L inverse format you can write this in this way also. Both are equal to each other. This I call the state transition matrix. State transition matrix. Very important. Okay, this we call the state transition matrix. So they can ask to form the state transition matrix also. They will give you the information like state equation. From the state equation you will take the a, you will put in this formula, and easily you can find out, isn't it? So wait a minute. So for this today's class it's enough. We'll come with the problems in the next class. For the new updates you can subscribe the Gatematic. You can find us on the Facebook for the doubt solving. We'll meet in the next class. Till then, take care and bye.